All right, in the last couple of videos, we talked about solubility, and in pretty much all of those, we talked about dissolving a solid into a liquid. We need to talk about solubility of gases. It is entirely possible to dissolve a gas into a liquid. Any of you who've ever had a carbonated beverage know that this happens. Not a big deal, okay? But it turns out that for solubility of gases, it really doesn't matter as much whether things are polar or non-polar. So it doesn't depend on polarity very much. So with solids and liquids, if you have two things that have similar polarities, they will dissolve together. For gases, it really doesn't matter. Non-polar things will dissolve in polar things all the time. That's actually what carbonation is. It's carbon dioxide, which is a completely non-polar thing, dissolving in water, which is very, very polar. It's mostly based on temperature and pressure. Okay, so we need to talk about each of them separately. Okay, so temperature, the idea is, we said that with solids, the higher the temperature, the more likely you are to overcome the intermolecular forces and dissolve everything. Great, makes perfect sense. With gases, the problem is high temperatures is what allows them to escape the intermolecular forces. So it turns out that for gases, they are more soluble at low temperatures, which sounds really counterintuitive, but if you think of it more about trying to trap things that are running around at the running around because of high temperatures, low temperatures allow them to move slower and be dissolved in the liquid. Okay. Similarly, if we talk about pressure, we're talking about interactions. So what we're visualizing is if you had, like, let's say you've got some water in a container. I don't know how to do this sideways. Great. What we would have is this is the water, and there's gases up here. To get these gases to dissolve in here, if you have it at low temperatures, they move slower, which means anytime they hit the water, there is less of a chance that they'll have the energy to escape. Similarly, when we talk about pressure, the more gas molecules there are up in this space, the more likely it is to dissolve down here. So it turns out that if you want gases to dissolve, you want really low temperatures and really high pressures. So basically higher pressures means more gas dissolved. So basically, if you're talking about solids, pressure doesn't matter much, but you want really high temperatures. If you're talking about gases dissolving, we want low temperatures and high pressures. So here's an example. I'm going to use this water bottle. This is not carbonated, but let's say it was. So if you bought a brand new 2 liter of Coke or Pepsi or whatever your style is, most people don't like 2 liters because as soon as you open them, it starts getting flat. You start losing gases that are dissolved. This is also why if you have a couple water bottles, if you have a 2 liter of pop, soda, whatever you like to call it, I'm gonna say pop because I'm from the Midwest, it doesn't actually look carbonated until you crack it open. As soon as you open it, the pressure inside has dropped because what's actually happening is this little liquid at the top, or this gas at the top, is really high concentration carbon dioxide. And when you crack that lid, this has escaped, which allows the dissolved carbon dioxide to also have a place to escape. Okay, you dropped the pressure, so the solubility dropped. Okay, so here's the idea. If you want to have a container of, say you've got a 2 liter of Coke and you want to keep it as carbonated as possible, what I'm going to tell you to do is pop it open, pour out what you need, and then when it comes time to contain it, you're going to crush, you're going to take the lid off, you're going to crush all of the air out. Now I just made this basically unrecyclable. And then you're going to put the lid on so that there is as little space up there as possible. You're trying to not give the gas anywhere to escape to. And you're going to store it in the fridge. Cold temperatures will keep it dissolved. And if you keep the gas in there gone, or keep a minimum amount of space in there, there's nowhere for the gas to go. Okay, so if you ever go to like little kids' birthday parties where like we got 2 liters of pop for everybody, and they just open them and leave them open, as long as they drink it in like the next half hour, it's really not going to matter. But if you're trying to keep this for like a week, like if you've got it in your dorm and you just have a refrigerator and you're the only person drinking it, you don't want to leave it open because the gas will escape. You don't want to leave it sitting out on the table because the gas will escape. You want to keep it as squished, so with as little air in there as possible, at as low of a temperature as you possibly can. Okay, I know I just ruined the recyclability of this bottle. Sorry. I'll try to reinflate it, I guess. Okay, another example of solubility of gases that I want to talk about, and I'm actually going to write some of this down, is something called the bends. Besides being a really amazing Radiohead album, it is also a concept that affects scuba divers. I have never been scuba diving. I have this horrible fear of drowning, so I have no intentions of ever doing that. Okay. The way this works is that at high pressures, so basically the problem is, I don't know whose phone that is, sorry. Whenever you dive, let's say this is the surface of the water. Whenever you dive, the higher the water pressure, as you go down, the amount of water pushing on you from above and from all directions is going to go up. So it's going to try to crush your lungs and make it harder to breathe. Okay? Well, to counteract that, you're going to need a scuba tank full of pressurized air. And the deeper you go, the higher the pressure of the air you're going to need. Okay? And that's not a big deal. You need high pressures to keep your lungs inflating properly, and you need it to breathe properly. But the problem is that we just said that at high pressures, things dissolve. So what happens is stuff that normally doesn't dissolve, like, I don't know, nitrogen. The atmosphere that you're breathing in right now is like almost 80% nitrogen. And almost none of it dissolves in your blood. Okay? But it turns out that if you're deep sea diving at high pressures, basically visualizes like scuba diving or a submarine or whatever. Nitrogen starts dissolving in the blood. This is, in and of itself, not even remotely dangerous. Okay, as long as you stay at that pressure. Okay. The problem is if you depressurize too quickly. So if you go from that deep sea level and go up to the surface too quickly, the pressure drops and this stuff becomes not soluble anymore. And if you depressurize too quickly, it'll go from being nitrogen that's dissolved to being nitrogen bubbles. Okay? And the bubbles can block off your veins. So, your veins are... Here, I'll draw a picture in a second. Let's write some of that down and we'll draw a picture. So if you depressurize too quickly, this is why they make you rise up slowly and exhale a lot to get that nitrogen out of your blood. There's nothing you can do to stop it getting in there, but you need to get it out. What happens is the nitrogen forms bubbles as it stops being soluble. It basically, if you drop the pressure, the high pressure made it dissolve. The lower pressures as you come back up make it form bubbles. The bubbles can form and block blood flow. And honestly, it can kill you. It's kind of like having an aneurysm. It is technically an aneurysm. An aneurysm is just an unexpected blockage, clot flowing through your veins in your head. This is the same thing, except it's a bubble. So basically what it comes down to is, suppose you have veins, hopefully you do, hopefully blood's flowing. Dissolved gases move with the liquid because they are dissolved. If you had a bubble of nitrogen form, it would impede blood flow, and basically nothing would go through here. It would basically block this, and wherever this is, there would be no blood flow to this area. It's kind of like, it's essentially the same concept as having a stroke, but instead of having like a blood clot there or fatty tissue or blocked on the word. What is cholesterol? Instead of having that type of blockage, it's literally just an air bubble that's blocking the airflow. So this is why if you ever go scuba diving, or if you ever go underwater at any great depths in a submarine or whatever you're doing, most of you won't, this is why they make a huge deal out of coming up very slowly no matter how much you're freaking out. So even if you've been like attacked by a freaking shark, you still have to come up slowly or your brain could rupture. Sorry. Yeah, but it's all based on solubility of gases. It's actually not a difficult concept. Low temperatures, high pressures mean dissolved. High temperatures and low pressures mean the gas starts bubbling back out. Okay, pressure tends to have more of an effect than temperature, but both of them together can cause a huge impact on this. So one option is, if you think somebody has the bends, you could in theory freeze them and it would dissolve the gas again and they might be okay. But freezing causes its own damage, and yeah, don't get the bends.